The name of this unit is called haloalkanes. It's 11.3C. The assessment criteria for haloalkanes is as follows. We'll need to understand the mechanism of a new kind of reaction, nucleophilic substitution. We'll be able to write equations and mechanisms for this nucleophilic substitution reaction, and we'll understand in a greater depth the concerns about haloalkanes and the mechanism of ozone depletion. Haloalkanes are named similarly to alcohols, where we have primary, secondary, and tertiary alcohols. We have primary, secondary, and tertiary haloalkanes, and they're named based upon how many functional groups other than hydrogen are attached to a carbon. And we'll see how this is represented as we discuss haloalkanes further. Because of the halogens, their boiling points are higher than the same kind of alkanes. Most haloalkanes are human produced. Only 40 to 60 of all the 1,600 are natural, and 40 out of those 60 come from plants known as fluoroacetates. We can make haloalkanes from alkenes, alkanes, and alcohols. There's a variety of ways to add a halogen across a double bond and instead of the alcohol to make haloalkanes. In order to understand how haloalkanes react, we must understand a new type of reaction. This is called nucleophilic substitution. A nucleophile is a negatively charged object. In this case, we're going to talk about nucleophiles being ions, and one of them being a halogen, which, with the exception of iodine, all of the halogens, fluor, chlorine, bromine, are more electronegative than carbon. That means that the electron pair in the carbon halogen bond, the carbon chlor bond, is dragged toward the halogen end, giving one end of the molecule a slightly positive charge and one end of the molecule given a slightly negative charge. As we know from term 1, this slightly positive and slightly negative charge is called an induced dipole. So, what happens when a negatively charged ion approaches a molecule of this sort? There are two things that can happen. We will have two types of substitution reactions. When we have a primary haloalkane, we will have a nucleophilic substitution 2 reaction, an SN2. Let's look at bromoethane. Bromoethane is a typical primary haloalkane. Because it has the halogen, and the halogen is more electronegative, the bond between the carbon and the bromine has an induced dipole. We will now have a negatively charged ion approach this molecule. We can call it Nu. That will be nucleophilic ion. Because the nucleophile is strongly attached to the positive end of the bromoalkane, it will move toward it. and it will get closer and closer until the nucleophile is firmly attached to the carbon and the bromine leaves as a bromine atom, or in this case, a bromine ion. Nucleophile moves toward the carbon end of the carbon halogen bond. The carbon end is positively charged. The nucleophile is negatively charged. They create a single bond, one between each other, and the bromine ion is expelled. SN2 reaction. Now, the same thing does not happen in tertiary haloalkanes. What's the difference between a primary haloalkane and a tertiary haloalkane? In a tertiary haloalkane, there is more carbon atoms blocking the ability of that nucleophile to get to where the carbon is in order to have an SN2 reaction. In chemistry talk, we call this sterically hindered. In simple English, the back of the molecule is cluttered with CH3 groups. What happens in this reaction is that a small part of the haloalkane ionizes to give a carbocation and a bromine ion. Once the carbocation is formed, it reacts immediately with the nucleophile. And the lone pair on the nucleophile is strongly attracted toward that carbon, which is called a carbon carbocation. So an SN1 reaction is a two-step. The first step is slow, where a small part of the haloalkane ionizes, and how we make it ionize determines that speed. And once that bromine ion leaves, we have a carbocation. The nucleophile finds that carbocation and creates a bond quickly. SN1. What about a secondary haloalkane? You'll see a picture down in the right-hand corner of what a secondary haloalkane looks like. It may do SN1 reactions. It may do SN2 reactions. So it all depends on the nature of the secondary haloalkane and its steric hindrance. This is a slide from one of the PowerPoints used in class that helps you determine when nucleophilic substitutions happen and what do they need or what encourages those reactions to happen. It's a good idea to have this in your notebook for use in the summative revision times and at the end of year revision times. Stop the tape and look at these three reactions. What do you think they are? SN1 or SN2? Ask your instructor and he or she will let you know. Now, there are environmental concerns with haloalkanes. Haloalkanes are fairly unreactive on the face of the earth at sea level, at the levels that we are at now. And that's why they were used in many applications, from using them as a refrigerant for refrigerators and car air conditioners to being used as fire extinguishers. However, when CFCs, which are haloalkanes that are multiply attached with chlors or fluors or bromines, once they get into the higher atmosphere, UV light finds them. And they react with UV light to form free radicals. Below you will see the 3 steps of the formation of a free radical and its reaction with other oxygen molecules and in the upper atmosphere. The following video will give you some idea on the effects of haloalkanes on the environment, and specifically the ozone layer in the stratosphere or upper atmosphere.
Ozone is a form of oxygen. An ozone molecule consists of 3 oxygen atoms. An ordinary oxygen gas molecule has 2 oxygen atoms. Most ozone is found in the upper atmosphere, where it is produced in small amounts, when the sun's high-energy rays strike ordinary oxygen molecules. The ozone molecules in the upper atmosphere absorb most of the sun's harmful ultraviolet rays before they reach the Earth. These rays can cause skin cancer and other health problems. A group of gases called chlorofluorocarbons, or CFCs, may pose a threat to the ozone layer. Chlorofluorocarbons are chemical compounds made up of atoms of chlorine, fluorine, and carbon. CFCs are used as refrigerants and to make plastic foam insulation. Because they are gases, CFCs can escape from poorly sealed containers into the atmosphere. Once CFCs are in the upper atmosphere, scientists believe a chain of reactions occur that destroy ozone. First, high-energy ultraviolet rays break chlorine atoms free from the CFC molecule. These free chlorine atoms can react with other molecules in the atmosphere. When a chlorine atom reacts with an ozone molecule, it steals one of the ozone molecule's 3 oxygen atoms, forming a molecule of chlorine monoxide. The remaining 2 oxygen atoms form an ordinary oxygen molecule. In this way, an ozone molecule is destroyed. Chlorine monoxide reacts easily with single oxygen atoms in the atmosphere, leaving a free chlorine atom that can destroy more ozone. Scientists estimate that 1 chlorine atom can destroy as many as 100,000 ozone molecules.
From the movie you just saw, you should have seen the mechanism of ozone depletion. You have a haloalkane in the higher atmosphere. You see in the example here that it's 3 chlors and 1 fluor on a carbon atom. UV radiation hits it, and one of the chlorine atoms break away to form a free radical. Now that chlorine atom comes along and hits an ozone molecule, O3, and the chlorine molecule takes one of the oxygen molecules. So that creates chlorine monoxide and O2. The oxygen atom, another oxygen atom, hits the chlorine molecule and makes O2 and chlorine, with that free radical able to make many, many more collisions. The problem is not in the fact that chlorine makes O2, but it poisons the reaction of O2 making O3. The creation of CFCs, or chlorofluorocarbons, is a recent arrival in our world. They were started in the 20s and 30s, and they have been released into the atmosphere. As they've been released into the atmosphere, the level of ozone in the stratosphere has decreased, and there have been worldwide agreements to reduce the amount of CFCs used by humans. Here are some questions to start your thinking. Alkanes are considered to be nonpolar, yet haloalkanes are much more polar. How does this affect the boiling and melting points? Look again at the examples of the mechanisms of nucleophilic substitution reactions and give an example of a nucleophilic reaction for SN1 and SN2. And thirdly, does this breaking down of the ozone layer by chlorofluorocarbons have an effect on global warming? What do you think?